This meeting is being recorded.
Okay, good afternoon, class. In this lecture, uh, we will start with the next unit, that is unit number 4, sequential logic circuits in CMOS. Okay. Screen is visible. Screen is visible. Okay. So, designing sequential logic circuits using CMOS. In that, what are different points that we are going to discuss? So, concept of latches, then SR flip-flop, different memory elements, D flip-flop. So all whatever the designs that comes under the sequential, okay, that we are going to discuss, and it's CMOS structure also, right? So all of you are aware of what is exactly sequential circuit. But now in this unit, we are going to discuss that sequential circuit with the in context with the CMOS. Okay, so this is what the central idea of this unit. Now, all of you know what is sequential circuit. Can anyone?
So it is depend upon present input and past output.
Right. Or in a simple language, you can say that sequential circuit requires some storage element or memory element. Why? Because it is depend upon the current state as well as the past state. Now the question is where that past state has to be stored, right? The question is where that past stage has to get stored. So for that, or to storing that, we require some storing element or memory. So in mostly cases, it's a D flip-flop. It's a D flip-flop as a storing element, or you can say as a register also, which can hold that data unless and until next clock pulse triggers the flip-flop. Then it will pass whatever the stored into the output, and it will let in the another input bit. So that's the general working of D flip-flop. So D flip-flop can be acting as a storing element or a register, you can say. Right. Now, this is what the general definition and general idea of the uh, sequential circuit. So what do you mean by sequential circuit? So first you have inputs, then outputs, then you have a next state that will get stored, then this have a current state. So this both next state as well as current state, it is important in case of sequential machine, because see, when you want to implement any FSM, finite state machine, so you require a different storing element to store the that particular state, right? So it doesn't matter you go for a Mealy type machine or a Murray type machine, no issue. But in both cases, when you are going to implement a finite state machine, so in that case you require a storing element. Okay, now in this chapter we are going to discuss the CMOS implementation of the most important sequential building blocks. So this is what different points that we are going to cover under this unit. So now I hope you are well aware of the what is sequential logic circuit. Okay, and what is combinational? So in case of the combinational, you don't have this extra feedback part, right? In case of combinational, you don't have this extra feedback path because you don't require that next states to be stored, or that becomes then the past state and it is the current state. See, this next state, once it gets stored, this will be the past state to the current state. Okay, so This pass state you don't require in case of combinational logic. It is required in case of only sequential logic, and that's why it's a major difference between the combinational logic and sequential logic is that combinational logic doesn't require memory element, whereas sequential logic requires a memory element. Am I right? So now the first part of this unit is a static latches and register. So how actually these static latches and registers are designed? So now you assume this two cascaded inverters. Okay, now all of you know the working of inverter and all that. Now you are well aware of. So now assume these two cascaded inverters. We have connected these two inverters back to back. Now this is the VTC curve of this first inverter. This is the VTC curve of this second inverter. Now when you combine this, right? When you combine this and plot together of this, see, if you combine this both, you will get this graph. Okay, when you combine this both, you will get this graph. Now what is the meaning of this graph? What is meaning? See, normally now you tell me, when we are talking about this VTC curve of this inverter, also this inverter, you can consider any graph. You either consider this one or this one. Okay, it is more or less VTC curve of a CMOS inverter, right? So this is VTC curve of this first CMOS inverter. This is VTC curve of this second CMOS inverter. So you can consider any graph. Now tell how many in a normal VTC curve of CMOS inverter, how many operating regions we have. In a normal course of this VTC course of CMOS inverter, how many operating regions we have? Can anyone will try to answer this question?
So 3.
No. 5, right? In the unit 1 only, I have explained this regions of operation. This is the region first, then region 2, this region 3, this region 4, and this is region 5. So a normal CMOS inverter of the normal CMOS inverter, so in its VTC curve have 5 different regions of operation. Now if you combine this both, now what you can see or what you can say, now only you have 3 possible operating points. Which one? This A, this B, and the middle one, C, right? You have only now the 3 possible operating points, this A, B, and C, right? So you can clearly understand from this diagram, right? So this is a VTC curve of this first inverter, this is VTC curve of this second inverter, and when you combine this, you will have this combined graph, and which has only 3 region of operations, this A, B, and C, right? Now a small deviation from this bias, now where its bias lies, this C, this midpoint is the biased point of this entire design. Now a very small deviation from this bias point, possibly maybe caused by the noise, is amplified and regenerated around a circuit loop. Okay, so very small deviation of this bias point can be that may be a possibility due to a noise, will get amplified and regenerated around this circuit loop, and the in the consequence to this, the gain around a loop being greater than 1, right? Now what is the resultant of this? The gain around this room will get greater than 1. The effect is demonstrated in this figure. Now have a look on this figure. Okay, this is the A, this is the B, this is the C. Now this is the deviation point, but because of the noise and other factor, this deviation point can move here and there, so as so as it can, right? It can make, or the resultant of this will is that the gain around that loop, it is greater than 1. Now the deviation is amplified by the gain of the inverter, and the enlarged divergence is applied to the second inverter and amplified once. Now that this gain of first inverter, which is already deviated, will get again enlarged and amplified, right? And it is again going into the second inverter. It is again going into the, or it is inputted, or it will get input to the second inverter. Now in that second inverter, it will get amplified once again. It will get amplified once again. Now the bias point moves away from the C until one of the operation points A or B is reached. And as a resultant of this, this bias point, that means this C point, will move to either A or B until one of the this point is reached. And in conclusion, C is an unstable operation point. That means because of this diversion and noise will get added, right? So this deviation of this bias point will get shifted, right, here and there. And what will happen, because of that deviation, the gain of this loop, it will go greater than 1. And as a demonstrate, this C will get moved towards either A or B, either A or B, unless it will get settled at either A or B, and so that the C will be the unstable operating point. Now the every deviation, even the smallest one, causes the operating point to run away from its original bias. And the chance is indeed very small that the cross-coupled inverter pair is biased at C and stays there. Right? That means the bias of this inverter is if ideally it should be at C, but because of the deviation, right? Because of the deviation, it is at A or B. Because of the deviation, it is either at A or B, right? Now the operation point with its property, it is termed as metastable. Okay, so operation of this C point, which gets unstable and which will go either at A and B, so this condition is called as a metastable condition, right, as shown here. So now on the other hand, the A and B, the stable operating points, right? Now that means this C is unstable and this A and B will be a stable operating points. Now in these points, the loop gain is much smaller than unity, where at A and B, at C, it is around this C, it is greater than 1, right? Around this C, it is greater than 1, but at A or B, it is much less than, or it is lesser than, or it is less than unity, much smaller than unity. Even a rather large deviation from the operating point is reduced in size and it will disappear only. Okay, hence the cross coupling of two inverter results in a bistable circuit, right? So, and this particular placement of these two inverter with series with each other, one after another, it's called as cross coupling. And so this cross coupling of this inverter results in a bistable circuit. Why bistable? So it has two stable points, which are those A and B, and C is always unstable. A is also stable, B is also stable, right? So it's a bistable circuit that forms the bistable circuit. Now in order to change the sorted value, we must able to bring the circuit from state A to B and vice versa, right? We must bring circuit from the state A to state B and state B to state A, vice versa. That is needed, right? Now how to do this? Now, since the precondition for stability is that loop gain, it should be smaller than unity. Loop gain should be smaller than unity. It's a condition that shows the circuit is stable. Now this condition is violated at point C, but at point A and B, this condition is fulfilled because at point A and B, loop gain is smaller than unity. That means these 2 points are the stable one. These 2 points are the stable one. Only C is unstable. Now, how to make this point unstable? So you have to increase the gain more than unity, then and then only these 2 points will get unstable. So how to do this? So if you want to bring a circuit from state A to state B or from state B to state A, you have to make this point unstable. Now how to make this unstable? So if you, for a short period of time, if you increase this loop gain larger than 1, right, for a short period of time, if you increase this loop gain larger than 1, it will get unstable. It will get unstable, and the positive feedback regenerates the effect of a triggering pulse, and the circuit moves to other side. That means in this case either from B to A or from B to A to B or from B to A, right? The width of trigger pulse need be only a little larger than the total propagation delay around the circuit loop, which is the twice the average propagation delay of the inverter. Okay. Now, in a summary, you can say this bistable circuit, has a two stable states. Okay. This bistable circuit has a two stable state. Which are those? This A and B, but by providing a trigger pulse, right, by providing the trigger pulse and making its gain more than unity, we are making this point unstable. But already basically these are the stable points. We are making that point unstable, and what is the resultant of that making unstable? It will move from B to A or from A to B, right, or from A to B. Now, in a summary, a bistable circuit has two stable states. In absence of any triggering, circuit remains in a single state. That means either in A or B, right? If you want to move from A to B or B to A, what you need to do? You have to provide a trigger pulse. What is use of that trigger pulse? The trigger pulse will enlarge the value of gain more than unity, so that will become unstable and it will get moved from B to A or A to B. This is how you can operate and you can design the latch, right? This is what the static latch or register, right? That means, see, once you have stored the data, it will become at B. Now once you have to output that data, your job is to simply provide the trigger pulse so that it will move from B to A or A to B. Now A will be the input and B will be the output, or vice versa. B will be the input and A will be the output. So you have to move from input to output. That's the latch. Now, next point is the SR flip-flop. Okay. Now all of you know how SR flip-flop works. Can anyone? How SR flip-flop works? How SR flip-flop works? So for 0 0, take first condition. For 0 0, what is the Q and Q dash? It's a Q and Q dash. For 1 0, Q will get shifted to 1. Q bar is a bar of this, that means 0. For 0 1 it will get 0, bar of this is a 1, and for 1 1 the both will be 0, but it is a forbidden state. But it's a forbidden state. That means the cross coupled inverter pair shows in the previous section provides an approach to store a binary variable in a stable way. However, extra circuitry must be added to enable control of the memory elements. Okay, fine. For the storing purpose, yes, you can just simply uh, add or connect the two inverters back to back, provide a triggering pulse. It will behave as a latches or a storing element. But to enable the control of memory, you have to add some extra circuitry. And the simple intercarnation accomplishes this is well-known SR or set reset flip-flop, right? How you can achieve this control using SR flip-flop, right? Now this circuit which we are showing here, it is very similar to the SR flip-flop by using the NOR based SR flip-flop. So these are the two NOR gates we have used, right? These are the two NOR gates we have used. So this cross coupled inverter pair with NOR gates replacing the inverter. Okay. The second input of the NOR gate is connected to the trigger input, that is S and R, right? So this second input of this S and R, it is connected with the this trigger input, right? This trigger input that make it possible to force the output Q and Q bar to a given state. Now these output are complementary. Okay, this Q and Q bar, these are the complementary. That means if Q is 0, Q bar is 1. If Q is 1, Q bar is 0. That means complementary. Okay, except the state that is S and R is 1 1. As I shown here, this 1 1 is a forbidden state in SR flip flop. When both S and R are 0, the flip flop is in the quiescent state and both output retain their value. Okay, for 0 0 the both flip flops are in quiescent state and it will retain the holding value, retain their value. That means a NOR gate which one of its input being 0 looks like an inverter and structure looks like a cross coupled inverter. If a positive pulse is applied to the S out input, the Q output is forced into a 1 state with Q on going to 0 and vice versa, and one pulse on reset the flip flop and Q output goes to 0. That means if we give S as a 1, right, so it will shift, it will exactly reflect to the Q and Q bar is a complementary of that. Now this R will become to 0, and if we force or if we reset or if you apply 1 to the R reset, then it will shift to the 0. That means this S, you can say it's a, but R it's a kind of inverter. See, for R it is 0, output is 1, and for 1 output is 0. That means this R reset is acting as an inverter, right? These results are summarized in a characteristics table of this flip flop. This table you can have a look on. The characteristics table is a truth table of the gate and list the output state as a function of all possible input conditions. That means 0 0 1 0 1 0 1 and 1 1. When both S and R are high, both Q and Q bar are forced to 0. That means it's a forbidden state. Since it does not correspond with our constraint that Q and Q must be complementary, this input mode is considered as forbidden state. Now, the additional problem with this condition is that when input triggers return to their 0 levels, the input triggers, that means S and R returns to their 0 levels, the resulting state of the latch is unpredictable and depends on whatever input is last to go low. Okay, now the SR flip-flops discussed so far is asynchronous. Whatever the flip-flop we have discussed is asynchronous. That means we don't have any clock pulse. But now If you add or if you apply a clock pulse, now it becomes a synchronous. Okay, most system operates in a synchronous fashion with transition event referred to a clock. One possible realization of this clocked SR flip-flop is a level sensitive positive latch. What is this? Level sensitive positive latch as shown in this. This is a level sensitive positive latch. Now, how it works? So it contains a cross-coupled inverter pair plus 4 extra transistors to drive the flip-flop from one state to another state and to provide a clocked operation. Now, it observes that the number of transistors is identical to the implementation, but the circuit has an added feature of being clocked. Now, what is drawback of this? The drawback of saving some transistors over a fully complementary CMOS implementation is that transistor sizing becomes a critical in ensuring proper functionality. Right now, consider the case where Q is high and R pulse is applied. Now consider this case, this Q is high and this R pulse is applied. Now what will happen? Now what will happen? The combination of transistor M4, M7 and M8, this M4, M7 and M8, that means this side, M4, M7 and M8 from a ratioed forms a ratioed inverter, right? What is ratioed inverter? That means in order to make the latch switch, we must succeed in bringing Q below the switching threshold of the inverter of M1 and M2. Where is M1 and M2? This M1 and M2. Once this is achieved, the positive feedback causes the flip-flop to invert the stage, and this requirement forces us to increase the sizes of transistors M5, M6, M7 and M8. So why we require this other 4 extra transistors? So reason is that to force the flip-flop to invert or to change its state. Now the present flip-flop does not consume any static power. In a steady state, one inverter resides in a high state while the other one is low. Okay, so this won't reply any static power consumption. Okay, so it is only resides or it is only what we can say operate between a VDD and ground, VDD and ground, because it's a static circuit. Okay, now multiplexer based latches. Okay, so this point we will discuss in the next unit, this multiplexer based latches. So latch, but we have to use a multiplexer and to form the latch. So how to do it, that we will discuss here, multiplexer based latches. So this point we will discuss in the next lecture. For today, for this lecture we will stop here. If you have any doubt or query, you can ask me right now.